This is structures and types of solids. We're going to be learning about the differences between ionic, metallic, molecular, and covalent network solids. So first, ionic solids. As you know, they are made up of positively charged cations and negatively charged anions, and they are held together by the electrostatic attractions between these ions. They are arranged in a 3D structure, which we call a crystal lattice. Here is what the NaCl crystal lattice looks like. It's made up of the Na positive ion and the Cl negative ion. The properties of ionic solids. Firstly, they have a very high boiling and melting point, which means that they are solid at room temperature. This is because the electrostatic attractions that hold the ions in the lattice are very strong, which means it takes a lot of energy to break these bonds. They are poor conductors of electricity, however, and this is because basically the electrons are fixed in place and they are not allowed to move around and carry charges. There is an exception, however, when ionic solids are molten or dissolved in water, then the ions are free to move and therefore they can conduct electricity. They are very brittle, which means when you drop them, they break into a bunch of small pieces. Like when you drop a block of salt, it'll break into a bunch of smaller pieces. And this is because oppositely charged ions repel when stress is applied. Here's a visual of what that looks like. So as you know, opposite charges attract and like charges repel. So in the crystal lattice, the ions are arranged in this alternating pattern of positive and negative ions. However, when you apply stress, this causes the like charges to line up and therefore they repel and then they break apart. Metals. In a metal, there are a bunch of stationary metal cations and they are surrounded by a sea of electrons, which is a bunch of mobile valence electrons that move around and they don't belong to a specific atom. They have a high boiling and melting point, which means they are solid at room temperature, except for mercury. And this is because the electrostatic attractions between the metals and these delocalized electrons is pretty strong. They are good conductors of electricity because they have the sea of electrons, so these mobile valence electrons can carry charges. They are malleable, which means they can be bent into shapes without breaking, and they are ductile, which means they can be drawn into wires. And this is because of the delocalized structure. Deforming the metal doesn't change the surroundings of the metal cores. Metals can also bond with each other to form alloys, and alloys are made when two melted metals are combined and then cooled. There are two types of alloys. First, we have substitutional alloys, which are between metal atoms of similar radii, for example, brass, which is made up of zinc and copper. And then we have interstitial alloys, which are between metals of vastly different radii. For example, steel is made up of carbon and iron. Carbon is much, much smaller than iron. Covalent or molecular compounds. These are atoms held together by covalent bonds, which are bonds that form between atoms of similar electronegativity values. They have a low boiling and melting point because the intermolecular forces between these atoms are very weak, so it takes very little energy to separate them. They do not conduct electricity because when they dissolve in water, they dissolve into molecules rather than ions, and they lack mobile charges. They are soft and flexible, although there are many exceptions, and this is because, once again, the bonds are very easy to break. And then we have covalent network solids, which are atoms held together in a lattice of covalent bonds. For example, diamond, graphite, and quartz, these are all examples of covalent network solids. They have a very high boiling and melting point because the covalent bonds between the atoms are very strong. They don't conduct electricity, once again, because the electrons are not free to move. They are localized in covalent bonds between particular atoms. And they are very hard because, once again, the covalent bonds between the atoms are very strong.